Hey, welcome back. In our last video, we learned a brand new way to determine if a reaction was spontaneous or not, if it was thermodynamically favorable. That new method was Gibbs free energy, or just free energy. It's basically defined by the equation of delta H minus T delta S. We said that if delta G was negative, then your process was thermodynamically favorable or spontaneous. It will happen. And so there are two different possible values for delta H and delta S. If your delta H was negative, that would be ideal because that would lead directly to possibly a negative delta G. And the other ideal situation was if you had a positive increase in entropy, which is always a good thing in terms of thermodynamics because that too, when coupled with a negative sign, leads to a negative value of delta G. We looked at various combinations. Maybe your entropy change was negative instead. In that case, you want to use small temperatures to minimize that unfavorable entropy change. Or maybe your enthalpy was positive. If so, and your entropy change was positive, then you want to do this at high temperatures to maximize your entropy to overcome your enthalpy to still get a negative delta G. In this new video, we're going to learn a couple new ways to find delta G. I think you'll find them pretty familiar looking, and it should go pretty quick. So we'll go ahead and get started. By the time we're all done, we're going to learn 5 different ways to find a reaction's free energy change. The first one is the equation we were just talking about, delta G equals delta H minus T delta S. We've been there, done that, so we'll check that off our list. Moving on, we'll get to Hess's law. If you remember, Hess's law is the thing where you can do alternative reactions, flip them around, multiply them, add them together to get the reaction that you want. So for example, in this case, the reaction that we really want is basically the combustion of sulfur to make SO2. To get there, though, we're going to use these other two side reactions. And again, we want to figure out what can we do to these side reactions to get our desired reaction. So as a reminder, I start with one term. In this case, we'll look at sulfur, solid sulfur. I look for it up here. I see it right here. It's in the right spot on the left side. It's got a coefficient of 1 just like we want. So I'm going to leave equation 1 alone here. No change there. Moving on, we got O2 in our equation next. Now O2 actually looks a little complicated because we have it in 2 different spots up here in our given equations. Because of that, I'm going to skip O2 and go on to SO2 instead. So we have one SO2 on the right, and our given equations, though, we have 2 SO2s and they're on the left. So to get rid of that, I'm going to multiply the second equation by 1/2 to change the 2 to a 1, and I'm going to do a negative as well. Let me rewrite that. So I'm going to multiply by a negative 1/2, which will both flip the reaction and reduce all the coefficients by a factor of 2. So let me just rewrite these then so that we can see more clearly what's going on. Okay, so there we have our 2 equations. Notice that the second one has been flipped around and multiplied by 1/2. Notice that we also multiplied our delta G by negative 1/2 as well, giving us a new delta G value of positive 71. Now we can add these together, and hopefully things will cancel out. 3/2 O2, that will cancel out with the 1/2 O2, giving us 1 O2. And so rewriting things, we have a sulfur drop down, we have a 1 O2 drop down, giving us a 1 SO2. And our free energy change of the reaction, it will be negative 300 kilojoules. So hopefully you remember how to do that. Pretty straightforward, pretty simple. We'll do one more example and move on to the next one. So in this example, we want to turn diamond into graphite. The equations that are given to us is basically combustion reactions. In the first reaction, for some reason, we are burning diamond to make a CO2, and that is a spontaneous reaction there. In the second equation, we're burning graphite. That's also a spontaneous equation too. I'll let you go ahead and work this one out, and then we'll meet back in just a moment. Okay, when you work it all out, you get a free energy change of negative 3 kilojoules. That means this process is spontaneous. So I'm sorry, ladies, your diamond rings will eventually turn into graphite. So, good news and bad news here. The bad news is you're going to lose your diamond ring. The good news is you can now write with it because it's graphite. The other good news is that this ain't going to happen anytime soon. Keep in mind that just because the reaction is spontaneous or thermodynamically favorable doesn't mean the reaction will happen anytime soon, or maybe even at all, because we also have our friend kinetics at work here too. And so if you think of the energy diagram for this thing, you have diamond going into graphite, which is thermodynamically more favorable. However, preventing that from happening is a huge activation energy. So that diamond ain't going anywhere, ladies. There's too much activation energy to start that whole process. And to see why, we can just take a look at the structure of these things, because as always, structure and form determines function. Okay, to see why the activation energy for this process is so high, we can take a look at the structure diamond here. So here's diamond. Each of these balls represents a carbon atom. Each carbon atom is bonded to 4 of its nearest neighbors in a tetrahedral pattern. These atoms are locked into place. They ain't going anywhere. In order to convert this to graphite, which looks like this, which exists of carbon atoms arranged in hexagons in these thin sheets here, you'd have to break most of these bonds and replace them with these bonds instead. That's going to take a lot of energy to do, so that ain't going to happen anytime soon. So therefore, even though it's more thermodynamically favorable to have graphite rings instead of diamond rings, your diamond rings are going to stay diamond for a long, 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 long time. All right, let's go ahead and look at the third method to calculate free energy, which should also look familiar, and that's free energies of formation, represented by the delta G F naught. Just like the enthalpies of formation, these represent the free energy changes if you were to synthesize a substance from its elements at standard conditions. So for example, if you were to synthesize liquid water from its elements of hydrogen and oxygen, you would release 237 kilojoules worth of free energy for every mole that you formed. In your books, it's tabulated as simply H2O, and then it gives you this value right here with your assumption that it really has this on the other side too. And so just like delta H, you do products minus reactants, and it should be pretty straightforward. So we'll go ahead and do example 3 and 4, and then you can check your work and see if we get the same answer. Okay, in example 3, same dealios. Don't forget the products minus reactants. Don't forget the coefficients. And notice that, again, we're back to elements having values of 0. That's because if you were to make an element from its elements, well, that's not much of a reaction, so there's no energy change, and delta G would be 0. Products minus reactants gives you a free energy change of negative 4172 kilojoules, and so yes, that is very thermodynamically favorable because your delta G is very, very negative. So moving on to example 4, this time we are synthesizing sulfur hexafluoride from sulfur tetrafluoride and fluorine, and this one's a little bit different because this time it gives you the value of delta G for the reaction, and we have to figure out the heat of formation of SF4. So I'll go ahead and let you read through it and work it out, and we'll compare answers. Okay, working through, we get a value of negative 731 kilojoules per mole for our heat of formation of SF4. And that, ladies and gentlemen, is all there is to it. And so in recap, we found 3 ways now to find delta G for a reaction. One is using the definition of free energy change, which is delta H minus T delta S. Method 2 was using Hess's law, rearranging equations, adding them together. Method 3 was free energies of formation, products minus reactants. And then stay tuned for methods 4th and 5th coming your way soon. Until then, I'll see you later.